Hello viewers, good morning. Myself Dr. T. Anodha. Today I am going to give you a video on a classical structure of atom. We will learn how to calculate various atomic parameters. This video deals with the fundamentals and every student of chemistry must be aware of this. For simplicity and ease of understanding, the whole video has been divided into so many parts noted here in slides 2 and 3. Introduction part. The structure of atom as we understand today emerged as a result of strenuous efforts made by a number of thinkers and scientists over centuries. Ancient Indian sage named Kadath is credited with the first ever proposition that every matter consisted of extremely tiny particles as its building blocks, and he named them as Kad, the Hindi term for the tiniest particle. However, British chemist John Dalton is recognized as the modern atomic theory originator. In 1808, Dalton had proposed that atoms were the ultimate building units of all matter. He had opined that atoms were indivisible. However, later studies revealed that atom is made up of several subatomic particles. In 1897, it was shown by experiments done by J.J. Thomson that negatively charged particles were emitted under appropriate conditions from cathode, and he had calculated their EIM, that is charge to mass ratio. During that very period, radioactivity was discovered, and it was shown that radioactivity emissions consisted of negatively and positively charged particles in addition to gamma rays. Thus, it was confirmed that atoms were divisible. They consisted of subatomic particles. Calculation of atomic parameters. First parameter, mass and charge, that is E by M, charge to mass ratio. This was calculated by J.J. Thomson. Considering the two opposite forces, when the path was provided with a magnetic field, deflection occurred. Here B represents the magnetic field distance, E is charge on the particle, U is its velocity, and mu square over R is centrifugal force. Equating these two, EIM can be given in the form of U upon RB. The magnetic force BEU could be counteracted by electrical field E, so that BEU equal to EE. Thus, U equal to E by B. Substituting for U in equation 2 gives EIM equal to E upon RB square. The unknown parameter R was measured by noting the deflection of a spot of light on a fluorescent screen. Both B and E were measurable variables. Thus, EIM was calculated, its value being 1.75 into 10 to the power 11 coulomb per kilogram. Next, we proceed how to calculate unitary electrical charge B. Robert Millikan did his famous oil drop experiment, and he was able to calculate the magnitude of charge E, as the presently accepted value is 1.602 into 10 to the power minus 19 coulomb, and electron rest mass is 9.1095 into 10 to the power minus 31 kilogram. The question arises as to why it is often called the rest mass of the electron. This concept must be clear to you. By rest mass, we mean the mass possessed by the particle when it is moving with a speed u is smaller than the speed of light. On the atomic scale, the rest mass of electron is 0.000548 atomic unit. Here U is the atomic mass unit. It is the unit of mass used to express atomic mass. 1 AMU is the average of the proton rest mass and neutron rest mass. Proton rest mass is 1.673 into 10 to the power minus 27 kilogram. Neutron rest mass is 1.675 into 10 to the power minus 27 kilogram. Atomic mass unit AMU is 1.67377 into 10 to the power minus 27 kilogram. Note that mass of proton is 1.673 into 10 to the power minus 27 kilogram, which is equal to 1.00722 atomic unit. That is 1836 times the mass of electron. James Chadwick had discovered neutron in 1932. It has no electrical charge. Its mass is 1.675 into 10 to the power minus 27 kilogram. It is about 1837 times the mass of electron. Surprisingly, neutron has non-zero magnetic moment, which is comparable to that of electron. This feature of neutron can be explained on the basis of its internal structure. Electron, proton, and neutron are spinning particles of quantum number half each. At high speed, the mass of a particle is given by Einstein's relativity formula, m equal to m0 over under root of 1 minus u square by c square. Here, m0 is called the rest mass. From this formula, it is evident that as speed u approaches the velocity of light c, mass of particle m becomes infinity. For the sake of simplicity, the rest mass of electron is symbolized by me or simply m instead of m0. Atomic models. Rutherford model and Bohr-Sommerfeld model. Rutherford in 1911 had performed a very famous experiment, infrared scattering experiment, using gold foil, and he was able to show that central part of the atom consisted of positively charged nucleus, which contains most of the mass of atom. Negatively charged particles electron are orbiting it. So it was the beginning of the classical atomic structure model. Dennis Francis Neil Bohr in 1913 had gone a step forward. He had come out with the concept of circular electron orbits of a specific radii as shown in figure 1. Figure 1, circular electron movement path. Central part is nucleus. Electrons are orbiting it. U is tangential velocity. R is radius of the first orbit. For an electron of mass m revolving around the nucleus, velocity u. The angular momentum m must be the exact multiple of the particle pi, where m is an integer. It was simply Bohr's speculation which has stood the test of time. Bohr model of atom was an important step in the emergence of modern quantum mechanics. He was able to explain the atomic emission spectrum of hydrogen gas. In 1915, Sommerfeld had come out with an extension of Bohr's model. He had suggested that the existence of elliptical electron orbits, in addition to the circular one, is possible. It implies, therefore, that the total energy of an electron in a Bohr orbit does not depend on the concept of exactly circular orbit. also on electrical orbits. Bohr electron orbits. Bohr electron orbits were symbolized as K, L, M, etc. cells, respectively for principal quantum number 1, 2, 3, 4, etc. An electron cell can accommodate up to a maximum of 2 square electrons, not more. When an electron of rest mass m is confined, moving with a speed u in an orbit of radius r around the atomic nucleus of charge plus Jd, the centripetal force is Jd square over r square, which is exactly balanced by the centrifugal force mu square by r. Mathematically, we can write Jd square over r square equal to mu square over r. Hence, from Bohr's second postulate, mu r equal to mh upon 2 pi. By substitution, we get u square n square equal to m square upon 4 pi square m square r square. From these equations, we can derive expression for radius Rm equal to n square h square upon 4 pi square divided m square. Note that this is the classical expression, not the quantum mechanical. In SI system, the equation takes the form Rm equal to 4 pi epsilon n square h square upon 4 pi square divided m square. Here 4 pi epsilon is called permittivity factor. Its numerical value is given here. By putting the values of various variables and constants, we derive the first Bohr orbit equal to 5.29 into 10 to the power minus 11 meter. That is 52.9 picometer. Total energy E of electron. Total energy E is sum of kinetic energy plus potential energy. And you can derive E equal to minus Jd square upon 2 Rm. Using the value of Rm, we find En equal to 2 pi square Z square Me power 4 n square H square multiplied by 1 upon permittivity factor square. The speed of electron in Bohr orbit of particle. From the equation mu r equal to n upon 2 pi, we calculate the speed u n equal to n upon 2 pi n Rm. By putting the value of various parameters, we derive the speed of electron in first Bohr orbit is equal to 2188 km per second. That is about 1 upon 1/50th the speed of light, less than the speed of light. Simple questions. Here in this question, we have shown certain calculations. Calculation of radius for first, second, hydrogen atom, and its comparison with those of lithium diapositive, beryllium tripositive species. So we have done the calculation here. The interesting feature is R1 for H compared with the R2 of triply ionized beryllium species. The second question is about energy expression. As we derived earlier, energy expression is given here. SI system, En equal to minus 2 pi square V Z square e power 4 upon n square H square multiplied equal to 1 upon permittivity factor square. Here mu is mass. Now we have again completed question number 3. Calculation of modified Planck constant, H cross, Rydberg constant, energy states, modified Planck constant H upon 2 pi equal to 1.055 into 10 to the power minus 74 joule seconds. Electron volt unit of Rydberg constant, it is 8.0 655 into 10 to the power 5 per meter equal to 1 electron volt. So we found its value 109,737 per centimeter. Energy calculation, the equation has been given here. By putting various values, we find that E1 ratio E2, E ratio E3, ratio E4 equal to 1, is 1 by 4, is 1 by 9, is 1 by 16, is 1 by R16, 4. You see, ignoring the minus sign, just for hydrogen atom, Z equals 1, the energy of electron in the nth boron orbit is given by the following equation. Minus 1 upon square into 13.6 electron volt. Then is the number of boron orbit. Or other species, Z is higher than 1, so energy is proportional to minus half Z square N square into 21.787 into 10 to the power 19 Joule. Coulombic law expression, force M equal to minus 1 upon 4 pi H9 Z square over R square, where R is distance in meter. Sommerfeld expansion model on board. Niels Bohr in 1913 had suggested that electrons keep moving in gently circular orbits around the positively charged nucleus, and only those circular orbits were permissible, on which angular momentum of electron is an exact multiple of quantum by, that is m equal to mass into tangential velocity into radius, mu r equal to nh upon 2pi, or n equal to 0, 1, 2, 3, etc. This is the figure showing the Bohr model. Obviously, there will be major axis and the minor axis, such that n upon k, that the length of major axis, the length of minor axis. Where n is the principal quantum number used by Bohr, and k is the essential quantum number used by Sommerfeld. Just as Bohr electron orbits or electron cells are quantized, when they are nh upon 2pi, so are Sommerfeld sub-energy levels or subsets in terms of k upon 2pi, like k 1, 2, 3, 4, 5. When k is n, the orbit becomes oscillatory. Note that k can never be 0, because in that case the minor axis will be 0, thereby implying linear motion of electron, which is not true. In modern uses, the essential quantum number is symbolized by L, and its value also includes 0. Here is the table. The principal quantum number 1, 2, 3, 4. The essential quantum numbers are given, possible numbers 0, 0, 1, 0, 1, 2, 0, 1, 2, 3. It may be noted that there are as many as n values of L from 0 to n minus 1. The integer symbol really is used for a Johnson quantum number, which is more appropriately called orbital angular momentum quantum number. And the names of subcells nowadays are sub-energy levels are orbitals. S n equal to 0, P n equal to 1, D n equal to 2, F n equal to 3, etc. and so on. So these are symbols taken from something which is spectroscopic characteristics. Thank you very much. Thank you. I hope this is the fundamental preliminary information, and every student should know this method best. By making few revisions, holding pen and paper in hand, you can easily understand them. Mastering these things is required. Thank you very much.